All right, let's get into the new lesson. So I'm just going to be going through some like details I didn't describe in lesson 6.2 with sigma notation, and we're going to be looking at some non-specific questions, so maybe not arithmetic or geometric. So it says sigma notation or summation notation, you can say sigma or summation, allows us to write a long sum in a single expression. The sigma symbol tells us that we are summing something. What we are adding together is not necessarily an arithmetic or a geometric sequence. So this notation is just saying you're adding something together. You don't know whether it is arithmetic or geometric all the time. We've looked at specific examples so far of what arithmetic equations look like and what geometric equations look like. So like we're pretty good at this point at like spotting those, but it's not always going to be like that. It's some kind of a sequence that has some sort of a rule attached to it, but not necessarily an addition rule or a multiplication rule. Just a quick reminder, the numbers on the bottom of the top and the top are telling you where to start and where to stop in your summation. And then this formula here is like the rule that tells you the pattern of the numbers that you're adding. Okay, so let's go ahead and do this one maybe a different way. When I look at this, I can tell that this is an arithmetic sequence, but maybe you don't notice that right away, and that's fine. So I'm going to give you another option. Your other option is this. Look at what you're doing. You're only adding 3 terms, right? First term, second term, third term, because you're starting at 1 and stopping at 3. So maybe it would just be easier to plug in and find those terms. So you're going to be doing plug in 1 to find the first term, plug in 2 to find the second term, and then you would be plugging in 3 to find the third term. So this is like all the math broken down for you and what it would look like. Simplify. So 2 times 1 minus 1 would be 1. So the first term was 1. 2 times 2 minus 1 would be 3. So the second term is 3. And then the third term would be 5. 6 minus 1 is 5. So your first term is 1, second term is 3, third term is 5. Add them up, and you get 4 plus 5. Looks like 9 to me. Okay, another factoid about summation notation. The variable n, in this case it's n, is called our summation index. When we evaluate a summation expression, we keep substituting different values for our index. So we're taking 1 as our starting index value, and then it's 2, 3, and then stopping at 4. So we're going to do this example as well, and I'm going to kind of do it the long way like I showed you before. And so this time, you'll notice our explicit formula. It does have a power, so it makes you think maybe it's geometric, but in fact it's not this time because the power is not changing. So it's not going to be a geometric sequence. It is a sequence, just not a geometric one. So how am I going to do this? Well, I'm going to start with the starting value, and I'm going to plug that in. And so that would give me the value of the first term. Then plug in 2 to find the second term. Plug in 3 to find the third term. Plug in 4 to find the fourth term, and we would stop at 4 because it says to stop at 4. What does that equal? 1 plus 4 plus 9 plus 16 with a total sum of, what is this, 25, 30? Right, 30. So the sum is 30. Okay, another factoid. We can start and end the summation at any value of n. For example, this sum takes integer values of n from 4 to 6. Okay, and we've never seen that before, but we do what it tells us to do. And in this case, it's telling me to start at 4 and end at 6. So I'm going to plug in 4 to find the first term. for fourth term, I guess. And then I'm going to plug in 5. And then I'm going to plug in 6. Remember, I'm plugging those values in for n into this equation. Okay, so that means the 3 terms that we're adding are 3, 4, and 5. 3 plus 4 plus 5 looks like 12. Okay, another factoid, we can use any letter we want for our index. So I told you a little bit before, sometimes you see, well, you see N a lot. Sometimes you see K. I is sometimes a letter that's chosen. It can be any letter that you want, usually a lowercase letter, but it could technically be any letter that you want to use. You just need to be consistent. So if you're going to use I in this spot, then your equation needs to have I's in it as well. So this one, the index is starting at 0 and ending at 2. So if we were going to set this up and show, all of our work, it would be starting with plug in 0 first, and then plug in 1, and so on. So I'll write this out. Those are times signs, by the way. I don't want you to think it's a decimal. Oh, stop. Too far, stroke. Plug in 0, plug in 1, stop at 2. So do the math. 3 times 0 minus 5, that would be -5. 3 minus 5 would be -2. And then 6 minus 5 would be 1. So we're adding up these 3 terms. That looks like it's going to be -6. Okay. Here's a weird question, and I put this one on here on purpose because I wanted to make sure we understood the connection piece between like the variables of the index and then other things. So down here, this variable is super important, and not the letter that you choose, but just that it's established. So this is telling you that n is equal to 1, and we're going all the way to 4, but the fact that it's n is telling you where to plug it in. And it's important in this question because we have 2 variables. We have an n and we have k. Well, if you're plugging in your index number for n, what is k? K is just going to be k. The index down here doesn't identify the number we're plugging in to be k. It says that its n is equal to 1. So the only number we're going to plug something in for is the n value. And your sum is going to have a k in the solution. So it's very weird, but I want to make sure you're checking that as you're doing your examples. So my first step is plug in 1, but I'm only plugging 1 in place of n. So that's what that would look like. And then plug in 2. And then plug in 3. And then plug in 4. And so we would simplify this down. We wouldn't be able to do a lot, but we could just call it k over 2 plus k over 3 plus k over 4 plus k over 5. And that, I guess we could get a common denominator and go further, but there's just no need. This would be your sum. That's good enough. Okay. Last little takeaway from sigma notation. Says before evaluating a sum in summation notation, always make sure you have identified the index and that you are only substituting into that index. Other unknowns should remain as they are. So it's just another example trying to warn you to look out for the letters. Okay, so this time the index is M. So we will only be plugging things in place of M. So let's go through this one just to do a little bit of extra practice and then you'll be done. So M equals 1 is our starting thing. So we're going to have 8k. I can't plug anything into k because k is not established as a changing value. And I'm plugging in 1 for M. Next, I'm going to plug in 2 for M. And then I'm going to plug in 3 for M, ran out of space. And then I'm going to plug in 4 for M. Okay, so this would give me 8k minus 6 plus 8k minus 12 plus 8k minus 18 plus 8k minus 24. This time I feel like it's totally feasible for us to go further and simplify. So I have 8 plus 8 plus 8 plus 8 would be what, 32k? And then I have 6, 12, 18, and 24, which would be 30, what, negative 60? Yeah, negative 60. So your sum looks weird, but your sum would just be an expression. It would be 32k minus 60. That's it. Make sure that you take your time on the homework assignment for this lesson. It is a Google form, and some of the questions are a little tricky, so I need you to make sure you take your time and really think it through. You're welcome to use a calculator, of course. And if you have any questions, let me know. See ya.